Hello, my name is Noah Salvador, and today we will be presenting our eVTOL's path towards a future without mobility or sustainability issues. Welcome to a world of wonder, where Wigeon flies by your side. But what do we actually want to achieve through the Wigeon? Following the requirement and market analyses, the team understood what our aircraft has to provide, which is a sustainable, personal aerial transportation for intercity travel that is competitive with the current transportation methods while requiring minimal infrastructure. The Wigeon is our solution. It has been designed to strive for excellence with a clean and modern finish. The typical flight with a Wigeon starts by boarding 4 passengers and a pilot. The Wigeon then slowly rises and then gradually transitions to gain speed. Then, low altitude cruising begins at 260 kph. Finally, the aircraft slows down, transitions and descends prior to landing at its destination. The batteries are then quickly recharged and the Wigeon is ready to fly again. The design of the Wigeon was carried through an MDF approach combining the efforts of 10 engineers. Each department constructed specialized coding scripts and were integrated together into an optimization problem. Today, my colleague and me will focus on the aerodynamic field of the design process. On this slide, you can see a top view of the selected configuration. Quite unconventional, the tandem wing configuration allows our aircraft to have the eVTOL capability. The individual wingspan, area, and separation were optimized with a script which constructed a design space based on the stakeholder requirements. The results converge into a design in which the wings have trapezoidal shapes. Although modeled independently, both wings have mostly the same characteristics. The wingspan and area are necessary for the generation of lift at low speeds. The length accounts for the cabin and other structural elements, and dihedral was added in different amounts to both wings, to be able to make the Wigeon maneuverable and controllable. Once again, the rest of parameters follow from set optimization program. Winglets are included in an attempt to increase the aerodynamic efficiency and maximize the range. The goal is to reduce the downwash induced by a tip vortex by combining the effects of the outboard rotating propeller and the winglet geometry itself. Winglet positioning differs between wings to reduce wing and propeller interference. But of course, the wing can't exist without an appropriate profile that matches the requirements to fly. To do so, a number of potential airfoils and their characteristics were evaluated and compared against using a trade-off procedure. We relied on weighted criteria, which were based on the required performance at low speed conditions. On this slide, you can now see selected parameters and scoring for the 3 most prominent airfoils, which best adapted to our requirements. The choice is immediate. This NACA 44 series offers the most versatile and efficient capabilities. It is worth noting that values for the lift-over drag ratio and CL max synergize the most with the chosen wing dimensions. The analysis of the wing performance was carried through a combination of methods due to the complexity of this aircraft. The tandem wing configuration leads to wing-wing and wing-propeller interferences. The iterative process was started with a modified DATCOM method to account for the tandem wings. Now, my colleague Alejandro will continue with the presentation.
Thank you, Noah. Now we will discuss wing-to-wing interaction. To analyze this phenomena, we use the lifting line theory, more specifically an extension known as the Weislinger-L method. We use this to calculate the span-wise lift distribution, the downwash, upwash, and induced drag. In order to do this, the velocity induced by the load vortex and the vortex sheet on the wings has to be calculated to obtain the induced angle of attack at a specific point. The results for the Wigeon aircraft are shown in the figure shown now. As expected, the CL of the second wing is lower, and due to the vortices of the first wing, the induced angle of attack is greater, which means that the implicit drag coefficient of the second wing is also greater. One important feature of the design is distributed propulsion. Hence, its effect on the aerodynamics of the aircraft has to be considered. For this analysis, only the effect on the total lift of the wing is included. To do this, we take into account that the slipstream of the propellers increases the flow velocity locally, which therefore increases the lift. This was quantified using a semi-analytical model by Boss et al., and the effects of implementing this in the CL alpha graph can be observed in this figure. As expected, the slipstream of the propellers increases the lift of the wings. Now we take a look at the aerodynamic center and moment coefficient. For calculating the aerodynamic center, we use the XFLR5 data of the Airfoil. from this we computed the Cm alpha and the Cn alpha curves of the airfoil by using a linear regression. Then from that we can obtain the moment coefficient, and after that apply a correction to take into account that now we're talking about a finite wing, not an airfoil. For the drag polar, we use the formula shown on the screen. The parasitic drag component of the fuselage, vertical tail and wingtips is computed using the component drag method. Then the pressure drag due to the fuselage upsweep is computed separately, and then the profile drag of the wing is computed using the data from XFLR5. Then also the implicit lift induced drag is included. The formulas for the different components are shown here. So for the component parasitic drag, the formula is shown now, and just to clarify, FF is the form factor of the component, and IF is the interference factor. Then we have the upsweep drag, which is shown now, and finally the implicit lift induced drag with the classical formula for implicit drag, and also a formula to obtain the span efficiency factor for a tandem wing aircraft. Now the drag polars of the airfoil and the entire aircraft are shown. As you can see, the most important component is the implicit lift induced drag. The aerodynamics for the transition between vertical and horizontal flight also had to be modeled in order to predict the energy consumption of the aircraft in this part of the mission. The aircraft was modeled as a point, so no moments were taken into account, and the lift and the drag were evaluated for the fuselage and the wings. They have to be evaluated separately because due to the tilt wing mechanism, the angle of attack of the fuselage and the wings are independent. Here you can see the resulting lift and drag coefficient graphs. The first two graphs are for the wing, and the final CD graph is for the fuselage. To model the post-stall behavior, the model proposed by Chauhan et al. Was applied. Now I want to take a look into the sensitivity analysis that we did. Here you can see the sensitivity for the positioning of the wings and its effect on the CL and CD. This was evaluated using Monk's biplane theory in order to observe the results with a different method than the one we used previously. We also wanted to evaluate the effects of assumptions, so we plotted how the lift over drag ratio at cruise changes depending on the wing tip efficiency, which is the KWL in the formula shown now on the screen, which was used to predict the effect of the winglets, and also the laminar flow fraction on the fuselage. Now I would like to end the video with a few recommendations for future research. So one of the recommendations we would like to make is to include the effect of propellers into the span-wise lift distribution. Furthermore, the estimation of the span efficiency factor could be improved for when the two wings are not very similar. We could also account for the interaction of tip vortices at the winglets and the surf from the propellers and its effect on the aerodynamic performance of the aircraft. And finally, we could also include the viscosity effects into the CL alpha curve of the propeller-wing interaction modeling. With this, I would like to finish the video, and I hope you enjoyed it, and thank you for your attention.